Check. Are we green light? There's green light. And we are. All right, cool. Waterfalls. So use the unit circle to define trig functions of real numbers. We're going to recognize the domain range of sine and cosine functions. Find the exact values for trig functions at pi fourths. Use even and odd trig functions. Recognize and use fundamental identities. Use periodic properties and evaluate trig functions with the calculator. Actually, before I jump into that, I want to go back real quick. There was formulas for linear speed and angular speed. Who has the linear speed? The first one. It's S over T?
Yeah.
So it was like a weird V, S over T, correct? And then you got an angular one, and that was like, it was a W, I think it's a Greek letter, W, and it was theta over T. And then you got another linear one, didn't you? There was like a second linear?
Linear from center, it's V equals RW.
V equals RW. And what I wanted to tell you guys was that they might be a little bit different from each other, but they're the same formula. In this case, what is S? Do you guys remember what S is? Do you guys remember the formula for S?
Theta R.
It was theta R, right? So theta R over T. And if you look at W here, what's W?
Theta over T.
Theta over T. Theta over T is here, so that becomes W, WR. See that? So it's just a play of formulas for you. So it's really going to be, you're going to use the one that best fits your scenario. You see that? You don't?
No.
Okay, we know that S is theta R, correct? So if we look at this linear speed one, this is S, which is equal to theta R. So if I break it down this way, it's theta R over T. We know that angular speed is theta over T, and that we have this other linear one that is where V is, or velocity is, RW. Well, W is defined as theta over T. Theta over T, sorry, that's not it at all. Theta over T is right in here. So this is theta T times R, isn't it? Well, theta over T can also be written as W. So this is really just R times W. So V, same one, R times W, theta over T. So yes, this is still the same formula, except instead of giving you S, which is theta over T, no. It's a weird play on that. Just a weird a play on all the different variables in there.
So what's the difference?
It really just depends what information you're given.
Wait, yeah, I have a question. What do you use these formulas for?
Rotations. So you're going to get some weird questions sometimes, like there's a record playing and it's like on a third song, which means that it's going to be at around a radius. What's the radius of a regular record? Anyways, it'll give you some radius like 2, and its angular speed is this already. You know, it might have you find the radius, which is what you're going to find from there, because the angular speed would be W, and then you're going to get R. And you might have to take that in and see what the linear speed is, how far you've traveled, that needle has to travel to play the whole song kind of thing. So it'll be a bunch of mixtures that you're going to take and plug in as you go with it. Okay? Or maybe another classic one is, you know, when you're on the Ferris wheel and it's traveling around and it's making some weird rotations. Not Ferris wheels. Anyways, but it's all going to have to do with rotations and angular speed and linear speed, okay? One of them is as simple as you are on a Ferris wheel with an angular speed of this. What distance have you traveled the entire ride kind of thing? Well, if you have the angular speed, you should be able to calculate the distance all the way around.
In degrees?
Well, they might give it to you in degrees, right? But you want it to be in radians in order to do it, okay? But I wanted you guys to let you know there's not two different formulas. It's just plugged in and mess around with a little bit, okay? Alrighty. I feel like we did this.
Wait, could you go back to the question?
To the here?
No, the one in between.
This one?
Mm-hmm.
Okay. Or did we start it and not finish it?
Yeah.
Is that what we did?
We stopped right when we got to donate.
Oh, this is why.
I think I'm like the top and half the cheese.
All by myself.
Just eat
No
it.
quiero estar.
I like this.
Oh my God, did you guys hear the breaking news?
What?
Frito-Lay has named their Cheeto dust.
What?
There's an official name for it now.
That's
Cheeto
disgusting.
dust?
No, it's called Cheeto.
Ew.
Ew, I hate that.
That's not gonna stay.
Wait, what? That's not how it is.
It's on the news. It's called Cheeto.
Someone pitched that idea and they were like, yes! Miss you.
Someone in my fourth hour says, so what's Taki dust called? Cheeto? It was funny in the moment, alright? Okay.
This role is weird. Half of us is going to World War III and half of us
This is
thinking
Munoz.
Cheeto does Cheeto.
What's up?
That seems like
You know, the
priorities
other,
are not straight here.
the other three have a family.
No, I didn't.
Except Cheeto.
I did not. Alright? It'd have to be a facilities recorder. Alright, great. Thank you. Peace.
I'll never
Quit
forget
leaving
it.
your Cheeto on my. Now I have to use the word, right?
But, like,
You left all your damn Cheeto on the desk. Alright, so you guys have these formulas already? Tell me where we left off here. We left off here. Alright, so have you guys seen the graphs for sine, cosine, tangent before? No?
Wait, does cosine go?
Here. So let me show you first. Let me show you first what they are supposed to look like. I have a poster over there.
Oh no, it's like the whiteboard. You see like
The little people.
the little arms, that's what the graphs are supposed to look like.
Oh, my pictures. Yeah, well, let me show it to you. Here.
Oh, there it is.
On that frame. You see the picture? The picture frame on the bookshelf?
Yeah.
That has it all in there. So, let's start with my favorite one. My favorite one is cosine. You guys ready? Let me square this off so it looks a little bit better. Zoom square. Oh, that's not it at all. Stop! Stop! Stop!
You do second off.
Window. So, shoot, I'm gonna have to go zoom. Standard first. Oh well.
It'd be like,
Oh well. You guys have seen these before? So this is, no? Well, if you have not, put this in your memory banks. This is what the graph of cosine looks like. This is what the graph of cosine looks like.
okay, I'm drawing the little people. Mine just looks
Wait,
a
doesn't
little-
tangent do that one where it go like this?
Tangent is weird. Tangent goes like, it's asymptotic.
Yeah, it's like.
Yeah, so it looks it looks like repetition of Q functions almost. Over and over and over and over. It looks like cubic functions over and over and over and over and over. Nice.
Yeah, but mine looks dumb. I don't want to talk about it. Stupid, so
Alright, so let's.
You know, the banana shell.
So here's what I want to show you guys. See how this says that the domain is from negative infinity to positive infinity?
Yeah.
Well, it kind of is, right? This thing is going to go on forever waving towards the negative infinity, and it's going to go waving toward positive infinity. And if you can see this is one tick mark below, right? That's as low as it goes. Same thing above. It only goes up one tick mark. Therefore, the range is going to be from -1 to +1. So
Brackets or-
your standard, with brackets, it's equal to. So your standard cosine function will have a minimum of -1, a maximum of +1. Its domain goes negative infinita and positive infinita. Just keeps waiting forever. Forever. Okay? So this is where these numbers are coming from. The true is for the sine function. The true is for the same is true for the sine function. They're both going to wave on forever, and their min and max are going to be from -1 to +1. Okay?
That's always true.
That is true. Well, unless you've shifted it, right? But the true is of the parent functions.
Can you like shrink it?
Yeah. Well, I have to be very careful here because can you stretch it and compress it?
Yeah.
Yes. So you can make it be smaller, or you can stretch it really wide so that it doesn't go -1 to 1. Kind of like what we did with parabolas, right? We would
Yeah.
stretch those as well. Same idea. We can still do that. So we can stretch them, or we can compress them. So yes,
What's the catch?
but they would still wave on for.
Why'd you laugh? Like, what's the catch?
No, there's no catch. It's just.
There's always a catch.
No, I was like, what's going on?
Nah, we'll break it down the way we have been with all the functions, and if there's any other additional information, then we'll see it as we go, okay? But I want you to be able to see where those bad boys come from. Okay?
That's cosine, right?
That was cosine. So here's what I want to do. I want to try to keep this a little bit simple. Let's see if I might. I'm gonna need to do this real quick. Okay, I want to do this real quick. That just gives me a little bit more space. Here, I'm going to sketch my unit circle. You guys cool with that? Okay, and I'm going to start at 0 degrees, and I want you guys to give me the coordinate for this. Like if I had a point, if I have my point right there, right? Give me the measures here, the coordinates. Yeah, it would be 1, 0, correct? And then you would have 30, 45, and 60 in your notes somewhere. You guys go with that? And then up here at 90 degrees, it would be 0, 1. And then you would have the other 3 that go in there. You guys are okay with those? Because we created those, right, last week? What about if I'm at 180? Or at pi, I should say. What would it be? -1, 0. And then you would have the other 3. And then I would have, this is it, which is at 270. Or 3 pi halves, if you will. This would be 0, -1. And then if I'm at 2 pi, I would be at 1, 0 again. You guys okay with that? Give me a thumbs up if you're okay with that. Thumbs down if you're not. We can still talk about that a little bit. All right, cool. So what I want to do is I want to sketch. Now, I'm taking you from the unit circle over to like an XY Cartesian coordinate system, right? Here it's a Cartesian, but we're kind of stuck in the circle mode. Over here, I'm going to go to XY, and we're going to actually graph some numbers here, okay? But my scaling is going to be in radians now. So that means I'm changing my scale to be by pi. You guys cool with that?
Sure.
Approximately what number would be here if this was like by ones? Approximately 3 something. So 3 would be like right under it, right? Don't understand that? If I was going to graph this in the real, 3 would be like right about here somewhere real close to it. Okay? But I'm going to go pi, 2 pi. Over here, here would be -2 pi. Here would be pi. What would this guy be? Half a pi? What would this guy be? 3 halves of pi? And of course, these would be -pi halves. This would be -3 pi halves. Okay? What did I say this one was we're working on first? I said I wanted to work on cosine first, right? And I asked you last week to associate cosine with one specific variable. It was x, right? So x is kind of sideways, and then what comes out is going to be the y value. So let's go to 0 radians. What is my x value at 0 radians? What is my cosine value at 0 radians? What is it? 1. So here I'm going to put a graph a point there, okay? Now I want you to go over to pi half radians. What's my cosine value there?
0.
It's 0? For those of you guys that aren't seeing it, over at 0 radians, my cosine value is the x, which is 1. So I graphed it there. Questions on how I graphed that point?
Explain it one more time.
Okay. This is 0 radians, right? This is your origin. And I'm graphing cosine, which is the x values. So at 0 radians, I'm going to be 1 for cosine. So at 0 radians, I went up to 1. Right? At pi halves radians, what's my x value now? So I graph 0 there. Right? If I go to pi, where am I going to graph at now? At -1. So that looks about right. So there's that piece, right? -1. Give me a thumbs up if you're following me.
Wait, but what's this for?
I'll show you a little bit. Some math magic. Wait a minute. You're not okay with those points graphing?
Why is that one at pi though?
This one? Is it too high? Too low?
I thought it was -1, 0, so it would be on the.
At pi halves, it's right here, right? Oh, no, wait, sorry, that's pi. At pi, my x value is -1. At pi, my x value is -1.
Okay, that.
What's my x value at 3 pi halves? 0? And then at 2 pi, where am I at now? I'm back up at 1. Okay? I want to make sure that you have these pieces. So please, give me thumbs up, thumbs down.
What's the vertical to x?
Say that one more time.
Never mind.
Never mind.
Why is X the vertical?
Why is x the vertical? We're graphing the values of cosine on here. Okay? So, remember, this isn't radian measure, right? How many radians have I traveled around my circle yet? 0. So when it's 0 radians, what's my cosine value? 1. Okay? Two different types of graphs. Unit circle. This is the Cartesian coordinate. So I could have gone 1, 2, 3, 4, 5, 6, 7, whatever. What I'm interested in graphing are the values of cosine. And that's what I'm doing, right? I'm graphing all the cosine values. This is a cosine. This is a cosine. This is a cosine. What would this one be? This would be a sine value, right? You guys okay with those? Now, if I went through and let's go pi quarters. Let's go pi quarters.
Why?
Because remember when we do input-output tables, the more points we have, the better? Correct?
Yeah, it'd be around half.
Okay. It wouldn't be half. It's radical 2 over 2, which is approximately, what's radical 2 over 2? Can someone do that in your calculator?
No.
This? No. I'm mad, grr. What's radical 2 over 2? Approximately.
0.707.
0.707.
707.
So right about here, it's like maybe right there?
Let's go with that.
I was thinking pi 6.
You guys close enough there? Okay. Can you guys see what I would do with all the other 3 points here? I would kind of create a graph. Here's what's going to happen.
It's gonna.
This is going to curve to hit this. And this is going to curve until it meets here. And then it's going to curve until it meets there. And finally it's going to curve until it meets there. And guess what you have?
Yes.
You have one revolution of the cosine function graphed here. So this is what one period, what one period of cosine looks like. Okay?
That's all period.
Period.
Oh,
With a D, then a T, all caps, and then a period. Period.
Period. Huh?
Who says that?
Question. Waterfalls.
Wait, how did you get that other little point again?
You're not getting waterfalls?
All right, I'll let you go and talk before I go on. Where did I get what point?
That little one
The one between 0 and 2 pi?
Yeah.
This one right here? So, between 0 halfway, I know it's not halfway, it's supposed to be approximately halfway, is pi quarters, right?
Yeah.
Pi over 4. Pi over 4,
Oh.
pi over 4 is 45 degrees. And we did these from the unit circle, right?
Yeah.
We said that that was radical 2 over 2 comma radical 2 over 2. Radical 2 over 2, according to Merrick, is approximately 0.74 something. So over here at pi fourths, I would go up about 0.7.
Okay.
And if I did 30 degrees, it'd probably be a little bit bigger still. And then 60 degrees would be a little bit smaller. So what's going to happen is this is going to create a bunch of points that are going to mirror this. It's going to look like that. I have a question for you. Let's say that I went a little bit further. And I went to the next part. So this would be like 2.5. Is that what it would be? 2.5 pi?
5 half.
What would my cosine value be? What would it be? 5 pi? 5 pi halves?
Well,
If I went over to 5 pi halves,
1. 0. 0.
what would it be? 0. Because it got to kind of come down, right? But that means I would be here, and I'd be just looking at that x again. So all I'm really graphing are all of the x values in repetition. So I'd go from 1 to 0 to -1, back to 0, up to 1, 0, -1, 0, 1. Let's go backwards. What's the value at negative pi halves, people?
0. I think
At negative pi halves, it's 0? What about negative pi?
-1.
-1, so I'm down here. What about negative 3 pi halves? 0. And at negative 2 pi? 1. So here you're going to see what you guys were seeing in the calculator, which is a graph of cosine. Okay? Questions?
I understand that sine is like the opposite of that,
No.
or it's like, well, now it's following the other ones, right? Like it's following.
It's following the y values.
That's what I meant. But like, what? How does tangent? I don't get how you get.
We'll talk about it.
Divided by y or something.
We'll talk about it. Because tangent, and there's a, remember I told you tangent was equal to sine over cosine? You remember that? Okay. So if I do sine over cosine, 0 over 1 is how much? 0. But when I get to here, 1 over 0 is undefined. So that means it becomes an asymptote. So that's what gives it that unique shape with all those different asymptotes. Because as you're doing that over and over and over. Okay? Question. Can you see why the domain goes from -1 to 1? So going back to your question, can it be stretched or not? Can it be stretched or not? I kind of already said yes, right? But that means that I would be working with a, yeah, absolutely. Nice and loud. The radius of my circle would be larger, or it would be smaller to create that. Now, misconception, sine and cosine, they're opposites of each other. They're not.
No.
They are not. Right on top of this one, I want to graph the sine function. I'm going to use red. Okay? Let's start at 0 radians. What's my sine value? 0 over at pi halves? 1 at pi? At 3 pi halves? -1 over at 2 pi? Back to 0, right? So it's going to do,
So like prettier.
okay? It's what?
Cosine a little to the left.
It's a little to the left, and it should make sense.
More to like the right.
Cosine's a little to the left. But you're not wrong. If you notice the pattern here, the sine, the cosine is always trailing or a little bit ahead, isn't it? Kind of just rotates, but that's what you're going to get. The sine is the cosine shifted a little bit.
A little to the left.
Tell me how much difference that shift is. How much is it shifted?
Half pi.
How much?
Half pi.
Half pi. Check this out. Check this out. Sorry. So here's my cosine, right? Let me square this because I really like it better when it squares. So there's this, right? Now, I want you guys to think about how we used to shift before. Do you guys remember when we had parabolas and we'd make them go either left or right? Okay? I want you to think about that and see how we can make the sine function graph so it looks exactly like the cosine. You already have all the numbers. Tell me what to write. Well, obviously we're going to start with sine, right? X minus 1? X minus 1?
X minus pi half.
Why minus pi halves?
Because that's how far it was ahead. So, wait, what are we trying to do?
Yeah, we want sine to look just like the cosine one.
So, if it was ahead pi halves and you bring it back pi halves, it'll be the same.
No, I agree with entirely what Evan says.
Well, this is how we learn, right? Let's mess around here. You guys ready?
Isn't it plus? Because it was to the right, it was ahead.
Well, let's take a look at the picture, and then you guys can decide again. Here is the cosine. Here's the sine function. Do we want plus or do we want minus?
We want minus. Wait, what are we starting with? Are we starting with go back to
Here's cosine. Okay.
maybe sine minus but cosine plus? That's right to me, but
Don't
I
count
can
the
be
random just stay on.
We're trying to get a graph where the sine one of that graphs ends up being right on top of the cosine one. So you can see that they're exactly the same curve. Push enter to see if we're wrong or right. No, you should already know.
trial and error.
What I tell you? I told you plus. That was like
What did this do?
Now they're opposites.
No, they're not opposites. They are not even inverses. It's a reflection of the other. Okay?
It's how do you do
So let's go back. I don't want that. So instead of minus, I should have done plus. There we go. Here's my cosine curve. And then I should get my sine curve.
I don't get it.
Yeah, I thought I was right.
What don't you get?
It has to be plus.
Oh.
I said that the same thing. I don't get why it's plus instead of minus.
Thanks. You should have told me that.
That's what I said.
I feel like that's something that you said.
Which way did it shift? To the left. So if I have a graph that is shifted to the left, I want it to shift to get back to 0, 0. I want it to go that way, right? So I want to do plus. I want to do the opposite of that. Okay?
Well, I don't thought I was right about something.
It's okay.
You were on the right track.
You're on the right track. That's pretty cool, y'all. Now, here's where it gets trippy. So here's sine, cosine. I'm just going to wait because I think we're going to do tangent a little bit. Here's what you need to know. Tangent it's just sine over cosine, right? It's opposite. It's opposite. Tangent is, what did I say it was? Opposite. Opposite over the adjacent, right? So if I do have a unit circle, it would be, if here's tangent, I want the opposite side, which is the y, over the adjacent side, which is the x. We already said this was the sine, and we said this was the cosine. So it would be sine over cosine. Okay? Wait. Y equals mx plus b. Wait. The square root of x sub 2 minus x. What?
No, it's just like.
Did you have an epiphany on something? Share it with me.
Something like that. Well, to find like slope.
This is what happens when you
Y
get
over
like
X, right?
unless he
Yeah.
gets stupid.
I don't know why.
Okay. Okay, yeah. If you made that connection, that's awesome. What's up? Of course you can. Alrighty. I think we've already done these, right? Oh, here we go.
Wait, I want to see tangent.
Yeah, do tangent.
Okay.
You guys don't know.
Whoa.
This is 1, 0. This is 0, 1. This is negative 1, 0. This is 0, comma, negative 1. Okay. So tangent is a little weird. You're not going to get as much shape from it. So you just need to know what the shape is going to look like, okay? So, you guys ready? Let's start at 0 radians. What did we say tan was? Sine over the cosine, right? So what is 0 over 1? It's 0. So, here's my point. Let's go to pi halves. On pi halves, what's 1 divided by 0? Undefined. So at pi halves, imagine that's not really there. We're using it as an asymptote. Okay? Let's go to pi. 0 over negative 1. 0 over negative 1 is undefined? It's just going to be 0. Let's go over to 3 halves pi. This is undefined. And then we're going to get 0 again, right? Can you guys see the pattern? Let's go the other way. What's going to happen at negative pi halves? Asymptote. 0. And then 0 again. So the question is, how does that really help me, right? Well, you're just going to have to know or remember what that shape looks like. It looked like this. Whoopah. So it looks like a bunch of cube functions repeated over and over and over, except the cube function is actually growing, Sebastian, while this one is asymptotic. So it's getting closer and closer and closer to its asymptotes, but it's never going to be the asymptotes.
So it is like the domain and range.
Did you read my mind? So here's the question then. Let's do the sign, because that's sorry, not the sign. Let's do the range first, because the range is the easiest one. What is the range here, yo?
All real name.
If you give it to me as an interval,
Negative.
parenthesis bracket. Good. Negative infinita all the way to positive infinita. Domain.
That's hard.
Nice and loud?
What?
I thought you said it. It's not intervals of 1. So this is what makes it a little bit tougher to write. Except for all the intervals of what? All the intervals of pi halves. So, because what happens at every pi half? You got an asymptote, remember? At every pi half, so this pi half, no, that's pi halves. At every pi, it was not every pi halves. Pi halves was, no, you're right, pi halves, that wasn't, JK. So every half pi, every odd, to be more specific, because this is a pi half, right? This is 2 halves pi. So at every odd interval of pi halves, you're going to get an asymptote. At 1/3, 3/3, sorry, thirds, what am I talking about? 1 half, 3 halves, 5 halves, 7 halves, 9 halves, you're going to get that asymptote repeat. Okay?
So how would you write that?
I think I have a slide with that on there. Maybe I don't?
Wait, no, that was it.
Was that it? No.
That's not it?
No.
Oh.
Here it is. But instead of 2 pi, it would be like that's not it. How do I want to do it? Let me find that notation for you. But that's all you really want to word. Okay. Let me make a note of that real quick. You know what? You guys do this while I make this note for myself. Given that the sine of some angle t is 2/3 and the cosine of it is radical 5/3, find the rest of the 4 that are remaining. That means find tangent, cotangent, secant, cosecant.
No way.
17.
And you know what? Just a hint. They gave you all the answers, yo.
The answers are right there.
Shut up. Shut up. Sorry. Sorry.
I'll let you guys struggle with that a little bit. You're welcome. My pleasure.
Sorry.
That's the, I was, my freaking was on the worm in my head.
You know what? I think it's in our next.
It's in the little. The little seashells.
That was easy.
That's like literally, and then the whale comes up. I don't think you're supposed to do it. Whenever number 3.
So are like the secants and cosecants, are they like the
Reciprocal?
yeah. So it's like if sine is opposite over hypotenuse, then is it hypotenuse over Dude, where did Haley go? I'm gonna
Oh, go on.
There's a domain, yo. It's all numbers except for all intervals of that. So, and it's all integers. So if you have like 1 pi, you'd have to add a half to that to make it odd, right? And then if you had like 2 pi, then you want the other odd one. So you're adding half a pi to every integer of n. So here's your domain for your tangent. Yeah, n.
Yes, I didn't write it as H. Obviously, it looks like an N. Why would I write H?
There's your domain. It's all x except for that, those intervals.
Wait, Lily, do you not know? Yeah.
I know opposite. No.
Lily. Really? What was it? Anybody's skill?
Wait,
I woke up from
Oh, this is your
You don't even have to do that.
I do.
You can do it with just like if you know what they are.
Yes.
You're a genius then.
I looked at my notes.
Oh, no, I'm thinking.
Waterfalls. So, I'm not a genius like Evan. I can't see things in my head like that. I'm very visual. So what I'm going to do is I'm going to create a triangle, and I'm going to put angle T on here. The sine is 2/3. That means the opposite is 2. The adjacent is Sorry, not the adjacent. Sine is opposite over hypotenuse. The opposite is 2, the hypotenuse is 3, correct? Cosine is adjacent over hypotenuse. So when I look at cosine, that means that my adjacent side is radical 5, and I just confirmed that that's still 3. So this is the triangle I'm working with.
Hey, I got that triangle.
So if I have sine cosine already, I just need
Are you
tangent.
doing that? I was like, why am I
Tangent
not
t.
doing it?
What's tangent? Opposite over
I got that one. I got
adjacent. So this ends up being 2 over radical 5. If you want to rationalize that right now, go for it. Right now I really don't care. I'm after all the other values. So now if we want cosecant, that's the reciprocal of sine. That's 3 over 2.
I got that. I did that.
The secant is the reciprocal of that guy. So that's going to be 3 over radical 5. And then cotangent is going to be the reciprocal of this guy, which is radical 5 over 2. But I like to draw this guy just so I don't make mistakes. Any questions on any of those?
I finally got something right.
Which one? No? Because everything's positive, right? So there's no, why would you get negatives? You will eventually, but remember, these are not opposites, these are reciprocals. The relationship on secant is simply hypotenuse over adjacent. So the hypotenuse over the adjacent is 3 over radical 5. Okay? Are we out of time again? Jesus Cristo. This is taking us, this is their day 3.
I lost track of days. I thought today was Tuesday. I was
It's not?
It's not. It's